I'm the publisher for these journals, and it's my pleasure to welcome our editors-in-chief of JWPE, Xiaocheng Wang, and Ludo Dumi, as well as the editor-in-chief of Desalination, Professor Sean. And Ludo will give an introduction of the journal and introduce our speakers for today. So Ludo, over to you, please.
Thank you very much, Luane. And thank you all for joining for our
recording in progress.
2025 webinars. Today, we are very lucky to be able to congratulate first GWPE 3-minute thesis competition that took place in October-November 2024. And the top 3 winners will actually present their work to us today. Before we do so, we have a brief introduction on the webinars and on some of the outreach programs that we have developed jointly with Desalination and the Journal of Water Process Engineering in the last 18 months or so. So first, on Desalination, obviously, Professor Tao He and Professor Hongping Shan are the 2 editors-in-chief. Desalination is focused primarily on the publication of publications related to papers on desalination and water treatment at large. It's one of the most prestigious journals in the water area, and you can see an impact factor in 2023 of 8.3 and very low, therefore competitive acceptance rates of around 29%. Desalination obviously doesn't completely overlap with what we do in GWPE, where we try to focus more on the water process engineering aspects and also water treatment without doing publishing materials on desalination technologies. In our case, we have been trying to develop for the last 18 months a number of outreach opportunities for students and also mid-career researchers. So we launched in 2024 the free MT competition and also a Trailblazer Award, and I think we'll be able to announce the winners officially in the next 2 to 3 months once their publications are through. We have been present and we welcome you obviously on the social media with LinkedIn, WeChat and Twitter, where we try to promote activities and hot papers. Both Desalination and GWPE have the same approach there. And we're going to have more joint events in 2025 as we move forward in the new year. Now, this is just a snapshot of the last 18 months, give or take, or nearly 2 years now, actually, of the webinars and the speakers we have had. So you can see we have been very lucky and privileged to have a number of top speakers. Some were editors, but the majority are actually not. They were researchers, people who have published in Desalination or GWPE, or obviously, for the talk in December, the founding editor in November of both Desalination and of GWPE, so Mayam Balaban and Nick Hankins. I will stop here because I think we have a busy schedule with the 3 speakers. I don't want to take too much time, but thank you once again for yes, maybe if you can talk a bit louder. Your voice is slightly faint for me. I'm not sure for the others, but...
Okay. Just the audio. Okay. Hello, everyone. My name is Jin Du, and I'm currently a 3rd-year PhD student at the Tsinghua University International Graduate School. It's a great honor for me to have been awarded 3rd place in the JW 3-minute page competition, and I am truly grateful for having this opportunity to present my research to you today. I would also like to express my sincere gratitude to the organizing committee for creating such a valuable platform for us to present our work and connect with fellow researchers. My presentation today is about microbial electrosynthesis systems for efficient CO2 reduction and acetate production. Let me start with a brief introduction about myself. My journey in environmental engineering started during my undergraduate years, and since then, I am deeply interested in the green and sustainable environmental biotechnology. After graduating from Tsinghua University, I pursued a master's degree at Tsinghua University. My research focused on enhancing anaerobic digestion by stimulating the direct interspecies electron transfer pathway. Then I continued my academic journey as a PhD student under the mentorship of Professor Xiaoyan Li. And so far, I have published 5 ICF papers as a first author, contributed to a book chapter, and been granted 2 patents. Now, I'm excited to share with you the details of my research today. First, I will begin with, here is the outline of my research. First, I will begin with an introduction to microbial electrosynthesis, providing some background on this emerging field. Then I will present 2 of my studies about reactor operation and cathode design for microbial electrosynthesis. Now let's dive into the introduction section. The greenhouse effect caused by the extensive CO2 emission is one of the most emerging environmental challenges we face today. According to the latest data, the global atmospheric CO2 concentration has constantly risen from a pre-industrial 280 ppm to over 420 ppm today. The alarming rise has led to severe consequences such as biodiversity loss, droughts, rising sea levels, and extreme heat. To curb the rising CO2 levels in the atmosphere, effective carbon emission control measures are essential. In addition, carbon reaction and the conversion technologies are urgently needed. Converting CO2 into high-value added organic compounds such as acetate can not only reduce carbon emissions, but also facilitates the recycling of CO2 into the industrial production, thereby contributing to the formation of a circular carbon economy. Although CO2 is a relatively inert molecule, the good news is that the microbial electrosynthesis offers a green and highly specific approach for CO2 reduction to organic products. The MES system combines electrochemical process with biotechnology. It features several advantages, such as mild reaction conditions, self-renewable microbial catalysts, and high product selectivity. This slide presents the fundamental principles of microbial electrosynthesis systems. The cathode acted as a working electrode and the microorganisms form a cathodic biofilm and convert CO2 into organic products like the volatile fatty acids. In contrast, the anode acted as a counter electrode, performing oxygen evolution reaction through water electrolysis. In addition, the anode can also be used for electrocatalytic oxidation, such as degrading wastewater. To conclude, the MES system is a hybrid of a bioreactor and an electrochemical reactor, which requires thorough understanding across its various aspects, such as reactor optimization, process control, and cathode design. These are critical aspects that we need to address in order to advance the application and development of the MES technology. So let's now move on to the first research focusing on investigating the impact of the inorganic carbon fading regime on microbial electrosynthesis. As autotrophic microorganisms in the MES systems use the inorganic carbon as their sole carbon source for growth, the inorganic carbon could be the strategy for supplying the inorganic carbon could be crucial for the efficiency of the MES system. The inorganic carbon could be provided in either gaseous CO2 or dissolved bicarbonate. However, the preferred form for the MES system requires further investigation. Therefore, the goal of this study was to investigate which form of inorganic carbon was more readily utilized by the MES system. To achieve this, we carefully designed 3 different inorganic carbon feeding regimes based on calculations including Henry's law and dissociation equilibrium of carbonic acid. As you can see on my slide, we operated 3 reactors in parallel. One was supplied with pure CO2 gas and buffered with baking soda. The main inorganic carbon source was gaseous CO2 for R1, while R2 was supplied with 20% of CO2 gas and buffered with the same amount of baking soda as R1. the main inorganic carbon source for R2 is the dissolved bicarbonate. For R3, it was supplied with 20% of CO2 gas, but with an additional dosage of baking soda to match the R1's total inorganic carbon concentration. Here is a photo of our experimental setup. Microbial electrosynthesis was conducted in a dual-chamber reactor. The carbon field acted as cathode, the platinum sheet acted as anode, and the cathode potential was controlled as -1 volt versus the reference electrode. Here are the results of this study. For R1, which used the gaseous CO2 as the main carbon source, acetate accumulation was observed after the operation for 50 days, with an average acid production rate of 93 milligrams per liter per day. In contrast, for R2 and R3, using the dissolved bicarbonate as the main inorganic carbon source, no significant acid accumulation was observed even after 140 days. Further, when the CO2 partial pressure of R1 was reduced to 0.2 atm, the acid production decreased and ceased. However, when the CO2 partial pressure was adjusted to 1 atm again, the acetate concentration resumed steady growth. These results indicated that the CO2 fixing bacteria in the amine system might prefer gaseous CO2, likely due to the higher affinity of bacterial membranes for gaseous CO2. Subsequently, we sampled the biofilm and the suspended microorganisms from the cathode chambers of the 3 reactors. The results expand the reactor performance in the previous section. First, the acetobacterium, the key CO2 fixing bacteria, is more enriched in R1, far exceeding the levels in R2 and R3. Second, the R1 exhibited lower levels of mesotoga, an acetate oxidizing bacteria, likely because the higher CO2 partial pressure inhibited the thermodynamic inhibit the acid oxidation from the thermodynamic aspect. Additionally, the presence of relative bacteria on the cathode was accounted with the characteristic of acetobacterium, the functional genus. To summarize, this research work highlights the importance of CO2 supplying strategy to the startup and steady operation of the amine systems. Our findings suggest that feeding more gaseous CO2 than dissolved bicarbonate would aid in the microbial CO2 electron reduction. The related paper is currently under revision after the first review by the JWPE journal. Let's shift to the second research focusing on the development of the biocompatible and electroactive bimetallic iron and manganese oxide cathode for enhanced amines. To realize high-rate microbial CO2 conversion, effective cathode materials are needed to satisfy both electrochemical and microbial demands. Surface modification with some transitional metal oxides can improve the catalytic performance of the carbon electrodes. We know that iron-based and manganese-based oxides are low-cost, abundant, non-toxic, and biocompatible. Moreover, the bimetallic oxides often exhibit superior properties compared to the monometal oxide because of the synergistic effects of 2 metals. That's why we chose iron and manganese bimetallic oxides for cathode modification in this study. So we modified the carbon field cathode with manganese oxide, iron oxide, and manganese fluoride bimetallic oxide. The manganese fluoride powder was synthesized through the co-precipitation and hydrothermal methods and loaded onto the electrodes by drop casting. Then 4 microbial electrosynthesis reactors using prepared electrodes were then operated. We first performed the physicochemical analysis of the modified electrodes. The XRD and the XPS analysis confirmed the successful synthesis of the manganese ferrite with the expected chemical formula, crystalline structure, and valence states. The three modified electrodes generally exhibited improved hydrophilicity, indicating better biocompatibility. As you can see, elemental mapping revealed a uniform distribution of iron and manganese elements in the modified electrodes. Furthermore, the BET analysis indicated that the manganese ferrite modified cathode had 2.2 times the surface area of the unmodified carbon field, also significantly higher than the modified cathode with manganese oxide and iron oxide. Next, we compare the in-situ electrochemical performance of the 4 reactors. Before the biofilm formation, the CV analysis showed increased electrochemical activity for the manganese ferrite modified electrodes. And after the biofilm formation, the EIS analysis showed significantly reduced the charge transfer resistance for the manganese ferrite modified electrodes, suggesting enhanced electron transfer between the electrode and the microorganisms. The acid accumulation in the 4 reactor reached 5 to 11 gram per liter, with the manganese ferrite modified group performing the best. Its average acid production rate reached 260 milligram per liter per day. The microbe community analysis supported the observed reactor performance results. It showed that in the manganese ferrite modified group, Acetobacterium accounted for 87% of the relative abundance in the cathode biofilm, significantly higher than the 51% observed with the unmodified electrodes. This increase is likely due to the enhanced electrochemical activity, larger surface area, and improved biocompatibility of the manganese ferrite. The SEM images reveal diverse morphologies having direct contact with the cathode. The nanowires resembling conductive pele were clearly observed, suggesting potential direct electron transfer from the cathode to the electroactive microorganisms. In terms of economic feasibility, the manganese ferrite modification increased the electrode manufacturing cost by only 21%, yet boosted the acid production rate by 2.8 times, demonstrating it as a simple and cost-effective modification strategy. Based on the above results, we propose a mechanism for the role of manganese ferrite in the MES system. The redox pairs of the manganese and iron work synergistically to promote the cathode and microorganisms electron transfer, thereby accelerating CO2 reduction to acetate. Additionally, homooxygens may utilize the hydrogen as evolved through the electrochemical hydrogen evolution as a reducing agent for the CO2 reduction. In summary, this research work has achieved microbial-driven CO2 electron reduction with a significant 2.8 times increase in acid production rate. The findings from this study has been published in ACI Sustainable Chemistry and Engineering. In the future, an integrated system by applying both biocathode and bioanode for environmental remediation purpose was worth investigation. For example, achieving simultaneous CO2 bioelectro reduction and sludge electrofermentation. In summary, these studies highlight the broad potential of using MES systems for CO2 reduction and resource recovery. However, further technological innovations are needed to enhance the efficiency of MES, such as improvements in cathode configurations and reactor design, in order to bring the world closer to the carbon neutrality. Finally, a heartfelt thanks to my supervisors for their unwavering guidance, constant support, and feedback. I would also like to extend my sincere thanks to my research group colleagues for their encouragement and collaboration throughout this PhD journey. I'm grateful to be part of such a dedicated and inspiring Li lab. Thank you for your attention, and I'm looking forward to hearing from you.